Okay, thank you. So we continue where we ended last time. So recall that we are aiming at an accurate bound for the number of solutions of an equation in two variables over FQ. That's the red goal. And as an auxiliary result, last time we proved this somehow, this vanishing result or non-vanishing result, whatever you want to call it. If you have a polynomial expression of this shape and it equals 0, where you have some control on degrees of the kij's, then all kij's must already be 0. And now we come to the key lemma of today, and that's really the polynomial method in action. So I write it in the general form that I need later. Let A be a polynomial of degree delta with 1 less than delta less than d minus 1. We keep the notation from above. And I want to count the cardinality of the set S, which is defined as follows. Let S be the set of X in FQ such that A of G of X times F of X equals 0. So it's all the zeros of F and all the zeros of G of F to the power Q minus 1 over D. Okay, and as usual in analytic number theory, we have a couple of parameters available that we optimize later. M is such a parameter, and we pick some M such that 3m squared plus m plus the degree of f is bounded by q over d. So I do it very precisely here, but you can just think of this as being like m is of size square root q over d. So think of this as m is roughly of size square root q over d. Okay, so then there exists a polynomial, a non-zero polynomial, and that's the polynomial method, are non-zero with a 0 of order at least m at every x in S. Okay, that's pointless. I mean, if I take the degree sufficiently high, this is very simple, but I have control on the degree. And degree of R is bounded by delta over d times qm plus 3 times q times degree f. Okay, and this gives immediately an upper bound on the cardinality of the set S. So this implies, in particular, that the cardinality of the set S is bounded by, so if every point has an order, has a 0 of order at least m, I can just divide all of this by m. So d delta over d times q plus 3q over m degree f. Okay, is this good or bad? Is this a good bound or is it a bad bound? What do we expect? So what's the number of zeros that we expect? Well, A has degree delta and G has degree f times q minus 1 over d. So the expected order should be delta over d times q, and that's what we get. So this is the expected order. And this should be seen as an error term. And here we see already a shadow of square root cancellation because m is roughly of size square root q, at least if d is not too large. and then we get something roughly like square root q in the error term. Yeah, so we see already that this is more or less what we want, except, of course, note the subtlety that this is only an upper bound. And as such, it's of course pointless to speak of expected order and error term. It's only an upper bound. It's not an asymptotic formula. We need a trick later to convert this into an asymptotic formula. That I will show you later. For now, we are satisfied with just an upper bound. Okay, so let's prove this. But again, I mean, you've seen this idea several times. The idea of the polynomial method is to construct a polynomial with control on the degree, having zeros of high order at every point in the set that you want to count. And this gives an upper bound for the cardinality of the set. Now, the whole magic of the proof is how to construct this polynomial. And as you have seen last week, I mean, this can be very tricky to come up with polynomials, and also very technical to come up with suitable auxiliary polynomials. So I just pull it out of the hat. Here is the polynomial. I define h of xy to be f of x to the power m. Okay, so this has zeros of order m at all zeros of f, times the sum I from 0 to d minus 1, j from 0 to k, where k is a free parameter that I will choose later, kij of x, g of x to the power I, and y to the power j. And then I specialize r of x, and that's my candidate polynomial, is h of x, x to the q. And the k's are not yet determined. We just know that, or we just require that the degree of kij is bounded by q over d minus the degree of f. Okay, and then I also need to choose k, and I choose k as follows. It's delta over d times m plus the degree of f. This is perhaps not an integer, so I take the Gauss bracket to make it an integer. And we'll see that I have no choice. If I want an optimal result, then this is the way I have to choose k. So there is nothing to choose here, really. All right, so that's the polynomial. And as in applications on transcendence theory, the idea is to have sufficiently many free parameters available. And these kij's, they are not yet determined, and we will determine them later. And we just need to make sure we have sufficiently many coefficients available in all the kij's to make sure that I can arrange it in such a way that I get enough zeros where I want. Okay, so this is my candidate polynomial. And we just have to check that it satisfies all the assumptions. All right, so first of all, what's the degree? So degree of r is what? Well, that's easy enough. That's bounded by m times the degree of f, plus the kij's have degree q over d minus degree of f, and then g has degree q minus 1 over d times degree of f. And the highest power is d minus 1. And then y is x to the q. So this is q times j, and the highest possible value of j is k. All right, and if you plug all of this in and just compute it, then what you get is 3q degree f plus delta over d qm. And that's precisely what I claimed here. So the degree is the correct one. And you see, in order to get this optimal result, the degree of r and m have to be in certain relation. Basically, the leading term for the degree must be this, because if I divide by m, I want to get the correct one. So, and you see this here, this will be the leading term and I have no choice for k. I need to make that choice for k in order to get the best possible result. Okay, the hard part is to show that I can arrange the kij's in such a way that I get sufficiently many zeros. Okay, so let's look at the zeros, and I detect the zeros by taking the Hasse derivative. And you remember we had this technical lemma that told us if I take the Hasse derivative of such a two-variable polynomial specialized to this situation, then I can just take the Hasse derivative with respect to the first variable and treat the second variable as a constant. Okay, also recall that G is a power of F. So really you have a high power, every term is a high power of F times a high power of X times this Kij. Okay, so in particular, we see that the Elf Hasse derivative of F to the power M times Kij times G is something like F to the M minus L, G of I, these are just other powers of F, times something else, Kij L, say, some other polynomial for 0 less than L less than M, where the Kij's have controlled degree, and it's easy to see that this is bounded by Q over D plus L minus 1 degree of F minus L. All right, so roughly you should think of this as Q over D plus M, more or less. All right, and so we get that the Elf Hasse derivative of R, this is what detects the zeros, is F to the power M minus L times some I from 0 to D minus 1, J 0 to K, Kijl, G to the I, X to the Qj. All right. Now, we want that this vanishes at certain points, namely at all the points where this holds. Okay, now certainly, I mean, we have already incorporated f of x, so we only need to worry about the first factor. Okay. Okay, so suppose z in fq is such that a of z is 0. Z is 0 of my polynomial a. So recall that a is of degree delta. So this has degree delta, which means that z satisfies an equation of degree delta. So it means that z to the delta can be written as a sum of powers of z with lower exponent. So this is c0 plus c1z plus c delta minus 1 z delta minus 1. There must be such an expression for certain cj in fq. And more generally, I can do this with any power recursively. So more generally, zi, I mean, this is the typical thing you do with algebraic equations, and you've seen similar arguments in transcendence theory too. You can write this with certain coefficients c0i plus c1iz plus and so on, plus c delta minus 1i z to the delta minus 1. Everything can be expressed in terms of powers of z up to delta minus 1. So now substitute z equals g of x. And so if x is such that a of g of x is 0, then we get So if a of g of x is 0, then the Lth has a derivative evaluated at the point x. And now we really evaluate things. This is not about polynomials, this is about elements in FQ. So this is f to the power m minus L at x. And okay, so what else do we have? We have a sum over I from 0 to d minus 1. We have a sum over j from 0 to k. We have kij super L. Now we use Frobenius. X to the power qj is really x to the power j, because a qth power is just the element itself. And then the g to the power I can be written as a sum t from 0 to delta minus 1. Sum ct I and g to the power t of x. All right. Okay, and we want this to vanish for L up to m. So want this to vanish for 0 less than L less than m. All right. Okay, let me slightly rewrite this as follows. So this equals f m minus lx sum st lx gt of x t from 0 to delta minus 1, where st is just the ij sum. So this is the ij sum ct I k I j l x to the j. All right, and you see that the degree of STL is bounded by, well, whatever bound I have for kij, and then plus the highest power, the highest value of j, which is x. And you see that these k's were bounded here. So we just copy that. That is q over d plus L minus 1 degree f minus L plus k. All right, and now it's a comparison of degrees of freedom. So how many conditions do I have, and how many free coefficients do I have in the kij's? Okay, so now compare degrees of freedom. So possible coefficients of the kij . Well, I can vary I have d values for I have k plus 1 values for j, and the degree is q over d minus degree of f plus 1, because I always get a plus 1 for free, because a polynomial of degree something has something plus 1 coefficients. Okay, and if you estimate this from below, you plug everything in. If you estimate this from below, then this is bounded by delta mq over d plus degree of f times q over d minus m minus degree of f. So that looks a bit complicated. Yeah, anyway, but really what you see, again, the leading term is delta mq over d, and then you have a kind of error term of somehow square root size. We'll see in a moment how this fits together. So this is the number of degrees of freedom that I have available. And how many conditions do I have in order to make sure that all these derivatives vanish? Now, how do I get this? What I want is that all the STL vanish. And so I need to make sure that all their coefficients vanish. So the number of coefficients of STL is, okay, I sum L from 0 to M. And now the degree of this guy is Q over D plus L minus 1 degree of F minus L plus K. And I have to sum this over T, and the possible choices for T is from 0 to delta minus 1, so I have delta choices. And if you estimate this from above, then this is bounded by delta times MQ over D plus 3 times M squared degree of F. All right, and now compare. We want that we have more choices, more degrees of freedom than we have conditions. And you see that the leading term is the same. So this and this coincides. And we want to make sure that this is bigger than that. And if you look at this, this is precisely our condition here. This is precisely the condition that makes sure that 1 star majorizes 2 star. And you see, I mean, if you compare this, this basically means that M squared is as much as, at most as big as Q over D, if you ignore lower order terms. Okay, here's a question in the chat. Correct, yes. I'm just by brute force. I want them to be all 0. And then in particular, all these, I mean, I don't see how to be more efficient. I just kill all of the STLs, and then the Hasse derivative at these points vanish. Yes. All right, and then just by linear algebra, I can make sure that all the coefficients of the S's vanish if I choose the Kij suitably, because I have sufficiently many degrees of freedom, and that's all that is required. And the key point is, if we scroll back, this polynomial has precisely the form of our lemma from yesterday. And so if this was the 0 polynomial, then all the Kij's would have been 0, but we have an overdetermined homogeneous system. So we can make sure that not all the Kij's are 0. Yeah? Okay. So find a solution with not all Kij 0, and this implies that R is non-zero, and it has the correct degree, it has the correct zeros, and it's not the 0 polynomial. So that's it. But you see, the fact that R is not the 0 polynomial in some sense is the hardest thing to prove. And this required yesterday's lemma, and this requires that y to the d minus f is absolutely irreducible. At this point, we haven't used anymore that y to the d minus f is absolutely irreducible. It was only used in the auxiliary result from yesterday. All right. So that is the key lemma. And yeah, again, I mean, the construction of this polynomial is somewhat tricky. But okay, once you have this auxiliary polynomial available, it does what you want. And again, you bound this set S, but it's only an upper bound. So a priori, this could be a completely useless result. It could be that S is the empty set, right? A priori, we cannot exclude the fact that S is the empty set. So a priori, this is not helpful. We need another trick to convert the lower bound into an upper bound. And that's the final theorem. So this is really the theorem.
Hi, Valentin. Can I actually ask you to pause and maybe explain conceptually what happened there? Like, it seems like we're bounding S by saying there exists a polynomial with all these roots, and so the number of roots can't be too big. On the other hand, the way that we got the polynomial at the end of the day was by counting sort of degrees of freedom and seeing that we had enough degrees of freedom. So that seems counterintuitive to me, right? Like somehow the number, you were saying we're bounding the number of roots because the polynomial shouldn't have so many degrees of freedom to give more than a certain number of roots. On the other hand, we're constructing the polynomial by seeing that we have so much degrees of freedom. So I'm just wondering where the sort of tension is coming from.
I'm not sure. I'm not sure I understand the question, because I mean, this H has an a priori, well, okay, it has something to do with the polynomial F. Well, okay, so I mean, inside the polynomial H is, of course, F and G, okay? But this H or R is just an auxiliary polynomial.
Right. I mean, is the trick somehow that you're looking at a polynomial of two variables, and so you're getting more degrees of freedom and then specializing to a polynomial of one variable?
No, this is just, I mean, you could have written this, I mean, no, this is really a polynomial in one. I mean, we never use the fact that it's in two variables. I could have just written this down as a polynomial in one variable. I only did this to make it clear that, like, how do we compute the Hasse derivative? And the trick is that the Hasse derivative is somehow simpler if there is an x to the q component, because that I don't need to worry about. That's basically the only trick, but it's really, I mean, it's a polynomial in one variable. I mean, this was just for somehow educational purposes that I wrote it in two variables.
Right. I guess what I'm saying is conceptually the reason that having a polynomial with lots of roots bounds. I mean, a polynomial of low degree can't have many roots, right? And so that's some sort of like counting of number of degrees of freedom somehow. If you want a polynomial with lots of roots, you have to have a higher degree so that there's more degrees of freedom to get enough coefficients to have a polynomial, right? On the other hand, the way that you constructed the polynomial was you said, oh, I have all these choices in the way that I constructed the polynomial, so I have enough degrees of freedom to have a polynomial. So that seems counterintuitive to me, that you kind of have enough choices for coefficients and then you're using it to bound the...
Well, I mean, in some sense, okay, I mean, in some sense, the result is maybe, okay, okay, somehow the result is not unexpected, right? I mean, I'm not proving anything that is spectacular. And so, I mean, I just get the expected order of magnitude as an upper bound, right?
Okay.
So in this sense, there is not much tension in this result. It just gives the expected order of solutions that I would expect anyway. Maybe the interesting point is that the error term, I mean, it will, in the end, it will all be about the error term, that the error term is sufficiently small.
Okay, thank you.
Okay, let me show you, because this is really an important trick. Because again, a priori, this lemma says very little if it's only an upper bound. Again, there could be absolutely no zeros, and then the result is pointless. So now comes really the theorem that I want to show. So take a polynomial, and suppose that y to the d minus f of x is absolutely irreducible. And suppose now we think of q as being big and everything else being small. So q is bigger than 100 times d times the degree of f. So we think of the degree of f as fixed and d as fixed, basically. Let n be the number of solutions, xy, such that y to the d minus f of x equals 0. Then n equals q up to a small error, namely 9 times whatever the constant is, d to the 3/2 times q to the 1/2 times the degree of f. And you can ignore for now all the constants. The only interesting fact is the q to the 1/2. We will later, so we need another trick to get rid of all the other constant and make this uniform. For now, we don't care about uniformity, we only care about q. Okay, so how do we do that? Proof? Okay, so we want to solve this equation, y to the d minus f of x equals 0. And we have to distinguish two cases, one of which is somehow trivial. If y is 0, then x must be a root of f, but there can't be too many, at most as many as degree says. So this is an easy case. The other case is more interesting. If y is non-zero, then f of x has to be a dth power in the multiplicative group of the finite field. Okay, so let n0 be the solutions with y equals 0. These are just correspond to the zeros of f. Okay, and for all other solutions, f of x is a dth power in fq star. So the d does not mean a default Cartesian product, it means a dth power. And since the multiplicative group is cyclic, without loss of generality, I can assume really that d is the GCD with d and q minus 1. So without loss of generality, d equals the GCD of d and q minus 1, because if not, then the dth powers are just the same as the GCD powers. All right. So let n1 be the set of x in fq with f of x to the power q minus 1 over d equals 1, right? And in this case, f of x is a dth power. So these are just the dth powers. And so in this case, I get d solutions for y, and this means that n is n0 plus d times n1. Okay, so far so good. Now comes the important trick. So recall that we have a factorization, z to the q minus z can be factorized. I can factor out z, and then I can factor out z to the q minus 1 over d minus 1. And then I'm left with a geometric series, z to the power j times q minus 1 over d, where j runs from 0 to d minus 1. Okay, and the observation is that the zeros of this polynomial are just all the elements in fq. So its zeros are just all z in fq. This is how you define fq. Okay, so the cardinality of the zeros is Q. In particular, Q equals the number of x in FQ such that f of x to the power q minus f of x equals 0. Okay, because this is just true for all x in FQ. And now you can split this into cases. First of all, f of x can be 0. This is what we call n0. Then f of x can be a dth power. This corresponds to this case. That would be n1. Or it can come from this term, and this is what we call n2. So this is the rest. So this is x such that sum j from 0 to d minus 1, f of x to the power j q minus 1 over d is 0. All right. And the trick is we can upper bound n1, but by the same argument, we can also upper bound n2 because that's of the same shape. But we know that their sum cannot be too small. Their sum is essentially q because n0 is bounded. Yeah. So their sum is relatively big. It's q, and we can upper bound both of them. And this is how we get the lower bound. So first, apply lemma 2.2 with the polynomial of degree 1, a of z is z minus 1 of degree delta equals 1. Then the set S that was bounded in that lemma is the set of x in FQ such that either f of x is 0 or g of x minus 1 is 0. So g of x equals 1, but g of x is just f of x to the power q minus 1 over d. And this is just n1. So this is just n0. So the cardinality, okay. So the cardinality of S1 is n0 plus n1, well, times d, because for each solution, and here I need, so for each solution in x, I get at most d solutions in y. Okay, wait, let's do this again. Let's do this carefully. So n equals n0 plus d times n1, and this is bounded by d times n0 plus n1, and this is d times the cardinality of S1. Okay, and now I can just apply the bound that that I got in that lemma, and if I just quote this, this is bounded by q plus 3 qd over m times the degree of f. Okay, so this is an upper bound for n, and now we get a lower bound by the same argument. So the trick is again that n2, for n2, we can run the same argument with a different polynomial a. So next, apply 2.2 with a of z equals 1 plus z plus and so on, plus z to the power d minus 1 q minus 1 over d. Then S2 is the set of all x in FQ such that either f of x is 0 or, well, this second thing here is 0. So sum f of x j q minus 1 over d is 0, j from 0 to d minus 1.
Valentin, is that last entry in A actually just z to the d minus 1? Because we
Say this
applied.
again, please.
Is the last entry in A just z to the d minus 1 because we apply it to G, which already has the power q minus 1?
Oh yeah, absolutely. Yeah, thanks, absolutely. Yes. Yes, of course. It should just be a geometric series up to degree d minus 1. Yes. Yes, absolutely. So the degree of that guy is d minus 1. So with delta, so delta is d minus 1. Yes, correct. Okay, and so the cardinality of S2 is n0 plus n2. And we obtain that n is n0 plus dn1. And that's greater than dn1, or greater than or equal to. But dn1 is d times q minus n0 minus n2. And so an upper bound for n2 gives a lower bound for n. So this is bounded by d times q minus d minus 1 over d times q minus 3 times q over m degree of f. And this equals q times. So see that, I mean, this is subtle. So you have d times q minus d minus 1 over d times q. So there's a lot of cancellation in these two terms. Yeah. And so what remains is 1 over d times q multiplied by d is q. So 3dq over m times degree f. Okay, and so we have an upper bound and we have a lower bound. And both of them have q as a main term and q over m as an error term. And I can basically choose m as big as square root q. So I choose m as big as I can, choose m to be q over 9d square root, and that's it. Okay. Yeah, so this is the trick how to get an asymptotic formula from only an upper bound, because the remaining part can also be estimated from above and the sum is just q. Okay, are the n's sets or numbers? The n's, oh, I had hoped that they are numbers. Yeah, they are numbers. Yeah, they are numbers. And so I think what I wrote is correct. Yeah. All right, so this is the main theorem. So once again, y to the d minus f of x has the correct number of solutions, namely the probabilistic argument says with probability 1 over d, we get d solutions. So all in all, we should get q pairs. And that's what the theorem says. Subject and up to an error term that is of square root size. And under the condition that y to the d minus f is absolutely irreducible, and we know that we cannot drop this condition. So this result is in some sense best possible, except for the fact that all the auxiliary parameters, d and the degree of f and all of that, they enter very badly. And I'll talk about this in a moment. Let me just, without proof, the proof is similar, state a companion theorem. So this would be used for multiplicative exponential sum or for multiplicative character sums, and for additive character sums, we have a similar result with a similar proof, but I don't go into the details. You can read them in Schmidt's book. It's very similar. The philosophy is exactly the same. So take a polynomial And for simplicity, I add an assumption that could be dropped, but that's a bit more tricky. Suppose that the degree is co-prime to Q. And in fact, less than Q. So let n be the number of solutions xy in fq star, in fq to the m squared, such that y to the q minus y equals f of x. Yeah, you see here that somehow the trace coming up, so this will be used for additive exponential sums. Okay, and then the result is that n minus, so you would expect q to the m solutions, and this is bounded by q to the m over 2 plus 4. So this is only interesting in large degree extension fields. So if the 4 is somehow negligible to m. Yeah. So if you start, say, with a prime field, q equals p, and then take a large extension field, in the large extension field, the count is very accurate. If you're just counting in prime fields, it's not very accurate because the 4 kills it. Okay, and the proof is similar. And you can find this in chapter 1.9. All right. So far, so good. So this is the first main result for the polynomial method in action. You see how to count solutions to to equations over finite fields very accurately. And what is not so good is the dependence. So somehow what I don't like is this factor and that factor. I would like to have something much more uniform in D, which will later be the order of the character, and in the degree of f. This method will not be able to achieve this. So we need another method and another trick. And this is something very beautiful. And this is a general principle. The idea is the following. It's a bit like with L functions. If you look at one single L function, it will never reveal its secrets. You have to view them in a family. And here we do the same thing. We view this point counting problem not only in the basic field, in the base field FQ, but also in a large family of extension fields. And within this family, there is a bootstrapping argument. And somehow we will get a self-improving estimate. So if we have a bound with arbitrary dependence in D and degree of f, it will improve itself and the dependence will magically disappear, simply by going up the tower in the extension fields. Yeah, this is an important trick. This is a very important trick that if you somehow take sufficiently high powers in so sufficiently high extension fields, then the bound will somehow improve itself. It's a bit similar. I mean, this is off topic now. This is only a footnote. But if you want to prove the Ramanujan conjecture, one way of doing it is if you look at sufficiently high symmetric powers. Yeah, and then you just need trivial bounds for each symmetric power. But if you take sufficiently high symmetric powers, this improves itself and eventually gives you Ramanujan. This is somehow the same idea here. Okay, and this requires some preparation. And I will already start to, in the last 10 minutes, with the preparation that we need in order to complete this program. And that's chapter 3. This is character sums and L functions. So we need L functions that capture the character sums that we are eventually interested in, that capture these L functions that capture the character sums over field extensions. Yeah, so we have a generating series that capture the character sums over field extensions. Okay, and let me just, so this is now a little dry, but let me just set up the stage by introducing the notation and the definitions. And maybe, okay, so maybe as a motivation, so just so that it's not so dry, let me maybe tell you what we eventually want to do. So eventually, we want to bound a character sum where we have a multiplicative character evaluated at some polynomial or rational function and an additive character evaluated at some other polynomial or rational function. Yeah, so this is a mixed character sum. A mixed character sum with an additive and a multiplicative character. Maybe you're only interested in multiplicative characters or only interested in additive characters, then you can just drop either chi or psi. But in the most general case, you have a mixed character sum. And the hope would be that under suitable conditions, this is bounded by something like some constant times square root of q. Okay, so that's the ultimate goal. And so, yeah, chi will be a character of order d. This is where the y to the d comes from, and psi will be some additive character. Okay, and yeah, so we keep in mind that we have an f and a g. The f goes into the multiplicative character and the g goes into the additive character. Okay, so now definition and notation. So this is just the preparation for tomorrow, for Wednesday, so that we can introduce L functions and get this bootstrapping argument. So a bit of notation. With G, and sometimes I write GQ, this is the group of rational functions which I can write as a quotient of two monic polynomials. Fqx, where h1, h2 are monic. So every rational function of that sort is in G, and if I multiply them, it's again of that sort, so this is a group. Okay, and so if I have a typical element R, a rational function in G, then I write this in canonical factorization as x plus alpha j, j from 1 to u, say, and then I from 1 to v, say, x plus beta I inverse, where the alpha j and beta I are in fq bar, so I factorize it in the algebraic closure, and not necessarily distinct, so I count them with multiplicity. Okay, now fix once and for all some polynomial f with m distinct zeros. So the nice thing is that the final bound will not depend on the degree of f, but only on the number of distinct zeros. So if it has multiple zeros, even better. Okay. And we write f is the product of x plus gamma k to the power delta k, where now we collect all gamma k's together that are the same. So the gamma k's are pairwise distinct. Gamma k in fq bar, pairwise distinct. Okay, I define G star, which is G star of Q, as a subgroup of G. This is the set of rational functions H1, H2, where neither H1 nor H2 has a 0 at gamma k. So where H1, H2 of gamma k is non-zero. So this has neither a pole nor a 0 at gamma k.
And that's for each k?
For each k, yes, for all k. Okay, and now I define a character. So for R in G star, define a character that I call following Schmidt, curly parenthesis R. This is the following thing. I evaluate f at the roots of R. So f evaluated at alpha j times f evaluated at beta I inverse. So recall, alpha and beta are the roots and the poles of R, and I evaluate f at these roots and poles. And this is the same as R evaluated at the gamma k, if you just plug this in to the power delta k. So this is a number, yeah? So this is an element in FQ bar, and in fact, it's not only in FQ bar, it's in fact in FQ because it's symmetric, yeah? So by Galois theory, that is, you see that it's actually in FQ. So this is a number. So to each rational function, I associate a number, okay? And later, so this will be used for a numerical character. Later, I use a character so that it becomes actually a complex number. Right now, it's a number in FQ. So, and this is obviously multiplicative. You see this from the definition. So obviously, R1, R2 is R1, R2. Okay, and we do the same thing on the additive side. This is for the multiplicative side. Now we do it for the additive side. So fix once and for all some polynomial g with degree of g equals n, and without loss of generality, because later I want to put it into an additive character, I can just move out a constant. So without loss of generality, I can assume g of 0 is 0, because it will later be put into an additive character. Okay? And for R in G, define R in square brackets is sum G of alpha j. So I evaluate j at the roots of R minus g of beta I. Empty sums are 0 as usual. So if there are no betas, then the sum is just not existent. And this is obviously additive. And again, by the same argument by Galois theory, this is not only in FQ bar, but it's actually in FQ because it's symmetric. So, and clearly this is additive. So R1 plus, R1, R2 is R1 plus R2. So this is something good to put into an additive character, whereas the curly bracket is good to put into a multiplicative character. All right, my time is up. So this was only a preparation for tomorrow. So the program is we will put this into characters, define the corresponding L functions, and then we want to see what happens if I extend this to higher extension fields. And this will give a self-improving estimate for our basic point counting. And this will finally give the best possible estimate for mixed character sums. Well, let's say, okay, so for mixed character sums, we need a little more than what we can do in this course. But at least we'll get a best possible bound for Klostermann sums. Yeah, so we will prove the best possible bound for Klostermann sums. We'll do this on Wednesday and Thursday. Okay, my time is up. That's all for today. Thanks for listening.
Thank you very much.